Hi, my name is Griffin Fletcher, and this is my Lab 1 report presentation. In this lab, I was tasked with observing the motion of an object constantly moving at the same velocity and to connect the object's motion with a fundamental principle, namely Newton's second law or the momentum principle. My experiment, the observation of the motion of a ping pong ball, compares the position as a function of time in an experimental case, specifically video observation of the ball's motion using Tracker, a computer program used to take an in-depth look at motion, and a predicted case using a computer model. Ultimately, when I compared the data produced by the two methods of observation, I noticed some striking discrepancies, which I will discuss, but it was apparent that the ball was moving at a constant velocity, which means that the net force was equal to zero. Newton's second law is outlined with this formula. Final velocity equals initial velocity plus net force divided by mass times the change in time. Because the object in this case is moving at constant velocity, net force must be zero. So final velocity equals initial velocity because the second term in Newton's second law will be equal to zero. Using the velocity found by Newton's second law, which we will call average velocity, position is calculated with this formula. Final position equals initial position plus the product of average velocity and the time interval. Here's my observation of the motion of a ping pong ball at constant velocity using Tracker. The x-axis is positive to the right. Here you can see the points of the ball's x position as a function of time, which are plotted on this graph. Here's the basic data used and found in the observation of my experiment. This video can be paused to take an in-depth look at the particulars of the experiment. The initial velocity as well as the position and time data I used in my models was obtained from the video analysis of the object's motion. It is worth noting that this initial velocity was calculated using the first and second positions and times instead of the first and last. This could have significant impact on my findings and will be discussed later. Next, I will discuss the predictive data produced by a GlowScript computer program model of the ping pong ball rolling at constant velocity. Here is an image of some of the code used to model the ball's motion. This is not all of the code, but this is the part that supplies the physical details that makes this program representative of my ball when run. Again, the video can be paused to analyze, but a few things are worth noticing. The initial velocity is in the negative x direction. The time step is smaller than that of the experimental data found with Tracker, which had a time step of 0.033 seconds. This will presumably yield data more accurate to the actual motion of the ball. Because this is a model of constant velocity, net force is set to zero. Finally, these two equations are basically a reproduction of Newton's second law and the final position formula derived from it, respectively. You can compare these to the actual mathematical equations, which are printed to the right. Here is a plot comparing my experimental findings derived using Tracker and the predicted findings generated by the computer program written using GlowScript. As you can see, a significant discrepancy emerges shortly into the experiment and only intensifies as the experiment continues. However, both the experimental and predictive findings are linear. This is evidence that the velocity did not change and that net force was truly zero. The differences in my experimental and predicted data could be because of several factors. First of all, the selection, by hand, of the ball's position using the Tracker software is imperfect. Secondly, the ball doesn't move perfectly along the x-axis. This is shown in this image of the ping pong ball at the end of the time interval and several subsequent position points, with the x-axis in purple. Obviously, the ball moves in the negative y direction as well as in the negative x direction. The final, and in my opinion, most likely possible reason is that I calculated the initial velocity using the first and second data points generated by Tracker. This may be a poor representation of the true average velocity of the ball, and using the first and last data points may produce a more accurate average velocity. To test this, I will calculate the second velocity and use it in my predictive model and compare the results to the experimental data. Here's another plot comparing the experimental findings and the predictive findings, but this time I used an initial velocity of negative 0.535 meters per second in the x direction, which was calculated using the first and last data points. Obviously, the results in my second plot produce far fewer discrepancies, and calculating average velocity using the first and last times and positions instead of the first and second is much more accurate. This makes intuitive sense. It seems that calculating velocity using the first and last data points in the experiment would give an average velocity truer to the actual average velocity than just using the first two data points. If the positive x direction were oriented to the left instead of the right, the velocity and position data would simply change signs. so the plot would feature the same slope but positive instead of negative, effectively multiplying the slope of the plot by -1. The predicted model generated by my glow script code contains ideal conditions. These conditions are nearly impossible to replicate in the real world. Lots of interactions of the ball with its surroundings are at play here, such as air resistance, friction with the table, and the possibility of the table being uneven. In reality, it is difficult to say how many forces add up to a net force of 0. It's worth noting that a portion of the experimental data in the second plot I generated, which is enlarged here, is a little off from the predicted data. It seems that in this area, the experimental data actually isn't perfectly linear. Could this be because the net force wasn't perfectly 0? Maybe, and the fact that the ball's mass was so small makes this seem even more likely, as this small mass may make the ball more susceptible to air resistance than a heavier object, such as a baseball, would be.